Good morning. This is Engineering Statistics and Linear Algebra 18 EC44. We are studying the Module 2, Lecture 6, Multiple Random Variables, and under that, some of the IID random variables. We already studied in the Lecture 1 the bivariate PDF and CDF. In the Lecture 2, bivariate expectations. In the Lecture 3, bivariate transformations. In the Lecture 4, Gaussian random variables. And in the Lecture 5, some of the two independent random variables. So in this lecture, we are studying about the sum of the IID random variables. So here, we are considering independent and identically distributed random variables. IID just means independent and identically distributed random variables, which are many. Some, when we say many different independently and identically distributed random variables. And what is the PDF associated with it? What is the mean associated with it? And what is the variance associated with this? All that we are going to study. So let us consider the sum of the different, instances or observations of the same random variable x. W is equal to sigma xi, I equal to 1 to n. Okay, n instances or n observations of the random variable x. So we know that the EFXI, that is the expectation of xi, that is expectation of x, will be equal to mu x, and variance of xi equal to variance of x equal to sigma x square. Also, the correlation e to the power e of the expectation of xi xj is equal to the e of xi square, when j and I both are same, is equal to e of x square is equal to mu x square plus sigma x square. And when they are not same, then it is just equal to mu x square, because at that time the correlation will be the what you call variance will be 0. If j and I are not same, then the what you call variance of x will be equal to 0. So therefore, we'll just get the mu x square. So let us consider n is equal to 2. That means w is equal to I equal to 1 to 2 xi, that is x1 plus x2. So under this condition, the expectation or the mean of the w will be equal to w2 will be equal to 2 of mu x. Variance of the w2 will be twice of sigma x square. And like you need to take the variance of w2, that will be equal to the variance of x1 plus the variance of x2. That will become the variance of x1 and x2 are both same, sigma x, because they are just observations of x. Hence, that will become twice of sigma x square. Similarly, when n is equal to 3, we can write w3 is equal to x1 plus x2 plus x3, and that is equal to w2 plus x3. This x1 plus x2 is w2, and then you have x3. So again, the expectation of this is equal to expectation of this plus expectation of this, expectation of this. We have already found it to be equal to 2 mu x. Expectation of x3 is same as expectation of x, that is mu x itself. So that will become 3 mu x. Similarly, variance can be found for w3, that will just become 3 of sigma x square. So continuing in this way, we can just say that if you have w is equal to whatever we have considered here, that is I equal to 1 to n xi for n what you call observations, small n observations, then we'll have the mu w, the sum of all the n observations will just give us the mu w is equal to n of mu x, and sigma w square is equal to n of sigma x square. Also, we see that the what you call if we take if you take two variables, then it will be just the convolution in the PDF. in the PDF. And as far as the characteristic function is concerned, the characteristic function will get multiplied. And since the, what you call the x1, x2, x3, and all that are considered to be the observations of x itself. Therefore, when we consider just two different observations, then it will be the characteristic function will be equal to multiplication of, again, phi x j omega and phi x j omega, that is phi x square j omega. Generalizing it for n different random observations of the random variable x, then the characteristic function for all of them together, the sum of all of them together, will just correspond to the phi x to the power n j omega for phi w j omega, where w is all the n instances or observations of x, sum of all the observations, n observations of x. So let us take some examples here. Here we are considering the exponential random variable given in the appendix A, which just turns out to be this: lambda e to the power of minus lambda x, x greater than or equal to 0, and 0 for x less than 0. So for this, the mean is equal to 1 by lambda, and the variance is equal to 1 by lambda square. The characteristic function will be equal to lambda minus j omega to the power minus 1. So we have already seen this as when we consider the two identical independent exponential random variables. This so the for the case of two identical random variables, we'll have the sum of the x1, x2 will just give us w equal to x1, x2 will give us f of w2 of w to be equal to lambda square w e to the power minus lambda w. Now, if we consider again the three different variables, x1 w equal to w3 equal to x1 plus x2 plus x3, then it will be just convolution of this with respect to fxx, or fxx with this are convolved to get the value, and we will get correspondingly as lambda squared u e to the power of minus lambda u, lambda e to the power of minus lambda w minus u du. So we have lambda squared here and lambda here, that will give us lambda cube. And again, if you solve this, this will just give you to the power of minus lambda, and it has nothing to do with du. So you can take out that. You are left with u du. U du will give you u square by 2 as the integral of that. And if you substitute the limits there, then it will become w squared by 2 over here, and this remains as it is. So then you'll get here lambda cube w squared by 2 e to the power of minus lambda w for w greater than or equal to 0, and 0 for w less than 0. So going in the same way, if you consider n different IID exponential random variables, then we'll get this value. That means in place of lambda cube, we had three variables, so therefore it is lambda cube over here. Three different observations. Here we have n different observations, or n IID exponential random variables, so therefore it will be lambda to the power n. And here we have w squared, so therefore here it will have w to the power n minus 1. And the e to the power of minus lambda w remains same as it is over here for w greater than or equal to 0, and 0 for w less than 0. The random variable w in this example is named the Erlang random variable of n. So this is the Erlang random variable of order n. And the different equations 3.93, 94, 95 are just the mean 93, 94, 95 are mean, variance, and the characteristic equation corresponding to that for the nth order Erlang random variable. And they will just turn out to be using all those three equations. We'll get mu w is equal to n by lambda, sigma w square is equal to n by lambda square, and the characteristic function phi w j omega is equal to lambda to the power n, lambda minus j omega to the power minus n. Let us take another example where we'll consider the Bernoulli's counting random variable, which is a discrete random variable. And again, from the appendix A, we can just check out the appendix A over here. The appendix A. So Bernoulli's random variable is this, right? Q del x plus P del x minus 1. And mu x will be equal to P, that is the coefficient of del x minus 1. Sigma x square is the multiplication of the coefficient of del x and del x minus 1. And phi x j omega, the characteristic function, is equal to Q plus P e to the power of j omega. Q plus P e to the power of j omega. That is what we have. So same thing we are using there. So here, if you see, we have written here mu x equal to P, sigma x square is equal to PQ, the phi x j omega is equal to Q plus P to the power of j omega. Now again, if we take here the n independent observations of the Bernoulli counting random variable, y is equal to sigma xi. So mu y will be equal to np. Mu y is equal to n mu x, and that is mu x is equal to p, so therefore np. Similarly, sigma y square is equal to n sigma x square, and n into sigma x square is pq, therefore npq. And the characteristic function will be equal to q plus p e to the power of j omega. So characteristic function for this is nothing but this to the power n, this to the power n, and that is what is shown here. Now let us come to the central limit theorem. Regardless, the statement of the central limit theorem is mentioned over here. Regardless of the distribution model, whatever is the distribution model, if we increase the sample size, if the sample size increases, the distribution of the sample mean converges to, the distribution of sample mean tends to or converges to the normal or Gaussian distribution. Okay. Distribution of sample mean converges to normal or Gaussian distribution. So let us consider here again the case of the Erlang PDF for n equal to w and lambda equal to 1. So at that time we'll have one, this will be 1 to the power 25, and lambda to the power 25 will be equal to 1 to the power 25, that is equal to 1 itself. W to the power n minus 1 is w to the power 24. E to the power of minus lambda is again 1, w greater than or equal to 0, 0 for w less than 0. The mean and the variance for this case is mu w will be equal to n itself, and sigma w square will be equal to the value of again n, because lambda is the mu w is equal to 1 there. Okay, mu w is equal to mu w is equal to 25, sigma w square is also equal to n, and that is equal to 25. So for this, we'll have the plot which is something like this. So this is your Erlang, and this is the Gaussian. You can see that they are almost, approximately same. So comparing the PDF for Erlang variable for n equal to 25, lambda equal to 1, mu w equal to 25, and sigma w square is equal to 25, we see that it's almost similar to the Gaussian random variable. So as we go on increasing the value of n, the Erlang will start almost matching with the Gaussian PDF. Now let us take one more example over here of a uniform random variable, between x between 0 and 1. So that is fxx is 1 between 0 less than x less than 1. So average of that will be half. Variance of that will be 1 by 12. This is the standard value. You can just find out again from the appendix A for the uniform distribution. Okay, uniform distribution, it is like this. With the mu x equal to a plus b by 2, a plus b is 0 plus 1 by 2. Here it is 1 minus 0 whole squared by 12, that is again 1 by 12. And you can definitely find this also, because where the b is 1 and a is 0, so it will be e to the power of j omega b minus 1 divided by j omega uh, b minus 1 minus 0, that is 1 itself. So we will get e to the power of j omega minus 1 divided by j omega as the characteristic function for the uniform random variable in our case. So we have got these two values. Now if we take two different realizations of x, that is w2 is equal to x1 plus x2, then mu w2 will be 2 by 2, that will be equal to 1. Sigma w2 square is equal to 2 by 12, that will be 1 by 6. And we will have the, if fxx is this, that is uniform, then we'll get w2 will turn out to be this function. Okay, if we extend it for w3, we'll get this function. Then if we similarly extend it for 11 convolutions, you are going to get this. So this will be tending towards 0, this will be tending towards infinity. So we will get a figure which is something like this, with 6 as the average and 0.4 as the peak over there, approximately. Because the what you call value here will just correspond to the 11 times of the value. So essentially what we have is here, here itself it is almost becoming like Gaussian. Here will be a perfect Gaussian over here. So f of w to w will be f of x in convolution with f of x, and that will give us the convolution of two different uniformly distributed functions, which will just turn out to be w2 0 less than w2 less than 1, 2 minus w2 1 less than w2 less than 2, and 0 otherwise. So this can be found out by convolving. Standard convolution procedure you can do. Both of them, please remember that they are uniform random variables between 0 and 1. They are fxx only between 0 and 1, and you need to convolve this. I hope you can do that on your own. So if you do that, you will get this. So please do that as an exercise, and so that you will get this value at the end. So continuing in the same way, if we go for w3 equal to x1 plus x2 plus x3, that is w2 plus x3, then mu of w3 will be 3 by 2, and sigma mu w3 squared is equal to 3 by 12, that is 1 by 4. So this is 1.5 and this is 0.25. Again, the convolution of the, to get the w3, then we will need to convolve the fx with the fw2. And we will get the function which is something like this. So again, please try to do this. That is the exercise for you. That is having got this value of fw2, and we already have fxx in the earlier slide. Okay, from here you take fxx and you need to convolve with this. If you convolve with this, you will get this function. Please try that as an exercise. So finally, we look at the sum of 12 independent realizations of x, and that will give us I equal to 1 to 12 xi. So mu w will be 12 by 2 equal to 6. So mean will be equal to 12. Sigma w square is equal to 12 by 12 equal to 1. So mean here is turning out to be 6, and that's what will be the case if you try to plot it. So almost again you will get it something like this. Almost you will get something like this. So according to the central limit theorem, the result FWW shown in the figure 3.13d is approximately Gaussian. The approximation turns out to be very good, and one can use Z is equal to sigma xi minus 6, I equal to 1 to 12. So this is sigma I minus mu x, mu w corresponding to whatever value you got. In the computer to simulate observations of the normalized Gaussian random variable Z, which has a mean of 0 and a variance of 1. Now let us consider averages. So in the averages, we'll take here y is equal to 1 by n sigma of I equal to 1 to n xi. So only difference is we had w here. Now y is w by n, or 1 by w into 1 by n into w. So effectively, you can just take that inside y is equal to sigma of xi by n, I equal to 1 to n. So the mean of that or expectation of that will just turn out to be mu x by n, and variance of that will just turn out to be sigma x squared by n squared. And if these results are used in the 3.93 and 3.94, then we'll get the value of sigma y is equal to n into mu x by n, and that is mu x itself, and sigma y squared is equal to n into mu x squared by n squared, that is sigma x squared by n. So these two are very much important. We'll get back the value of mu x here, whereas here the mean is divided by n, so mean is reduced. So the mean of y is same as x, and the variance of y decreases by a factor 1 by n. And as we have seen with the central limit theorem, y tends to be Gaussian with the given mean and given variance. So if n tends to infinity, the variance will just go to 0, and the mean will be same as the average, or the average what you call variance will turn out to be 0 as n tends to infinity, whereas the average so to say mean of that average function will just turn out to be the value same as the mean of x. So let us take an example here of the mean of x to be equal to 2 and variance of x equal to 0.5. We need to find, the PDF for the x is not otherwise specified. We don't know the PDF, only the mean and the variance are given. Let n is equal to 120 independent occurrence of x as used in the sum, then w is equal to I equal to 1 to 120 xi, then naturally mu w will be 120 into 2 equal to 240, and sigma w squared is equal to 120 into 0.5 equal to 60. If you take the averaging function, then y is equal to 1 by 120 of sigma I equal to 1 to 120 of xi. So under that condition, we'll have the mu y same as the mu x itself, because averaging will give you the same value, but the mean, the variance will get divided by the value of 0.5 divided by root of 120. The root of n is what we'll get for sigma x squared, and that will give us the value which is 0.0456. 0.0456. Let us take one more problem. The random variable u has a mean of 0.3 and variance of 1.5. The mean and the variance of y are, find the mean and the variance of y if y is mentioned like this. So here it is averaging. So we are given mu x is equal to 0.3, mu u, sigma u square is equal to 1.5. Or here, this is the average. For average, the mu y is equal to mu u is equal to 0.3, whereas the sigma y squared is equal to sigma u squared by n, that will give 1.5 by 53 is equal to 0.0283. Sigma y squared is equal to sigma u squared by n equal to 1.5 by 53 equal to 0.0283. So for this, you need to divide by the value of the what you call mean will become, in this case it is 60 over here. Here in this case it is 0.5. So variance will be the 0.5 value. 0.5 will be divided by, just check it up whether it should be divided by root of 120 or just 120. Just check it out. I'm getting confused. Okay. So if you take the sum, naturally that will just correspond to n mu u, that is 53 into 0.3 equal to 15.9. Sigma z squared is equal to n sigma u squared is equal to 53 into 1.5 equal to 79.5. Let us consider another example where x is a random variable with variance 1.8 and mean equal to 14. Why we are considering it as x minus mu x, that is shown here as the value 1 by 100 is equal multiplied by sigma of I equal to 1 to 100 by into I equal to 1 to 100 by I. So that is, this is mean here. That is the mean of y. Z is the mean of y. So the expectations of y will be equal to expectation of x minus expectation of mu x, that is mu x in minus mu x, that will turn out to be 0. So mu x is given 14, sigma x square is given 1.5, mu y will be equal to mu x minus mu x equal to 0. Sigma y will be equal to sigma y squared will be equal to sigma, that is variance of y is equal to variance of x minus mu x, that is variance of x minus variance of mu x is equal to 0, and we'll get just variance of x over here. Coefficient of x is 1, therefore we are writing here 1 square. If it was ax here, then variance of y will be equal to a squared variance of x, a squared variance of x. So a is here 1, coefficient of x is 1. Therefore, we have here 1 squared sigma x squared. That will just turn out to be 1.8. So because this is mean over here, the what do you call average over here. So the mean of z will be same as the mean of the y, and the mean of y is 0 here. Therefore, mu of z is equal to mu of y is equal to 0. Whereas sigma z square will be sigma y squared divided by 100. That will give you 0.0180. The random variable z is uniformly distributed between. Next example is random variable is uniformly distributed between 0 and 1. The random variable y is obtained from z as follows. Y is equal to 3z plus 5.5. Again, we take the average of all of them, 100 samples. So we need to estimate the probability of u less than 7.1. And if 1000 independent calculations of u are performed, approximately how many of these calculated values for u would be less than 7.1. So now if you consider this over here, right, the mean of uniformly distributed function z will be equal to half. Between 0 and 1 will be 1 plus 0 divided by 2. That will give us the value half. Similarly, the average will be 1 minus 0 whole squared by 12. The variance will be 1 minus 0 whole squared by 12 for z. And that is what is mentioned over here. Mu z is equal to 1 by 2.5. Sigma z square is equal to 1 by 12. So it is really speaking 1 minus 0 whole squared by 12, because limits the values of a and b over here are 0 and 1. Now, if you take the variance of the mean of this and the variance of this, mean of y will be equal to thrice of mean of z plus mean of 5.5 will just turn out to be 0, because this is just a constant. So mean of y will be 3 times of mean of z. Okay, mean of y is, mean of 5.5 is 5.5 itself. So 3 mu z plus 5.5, that will give you 3 into 0.5 plus 5.5, that will give you 7.0. So mean of y will be equal to 3 mean of z plus the mean of 5.5 is 5.5 itself. Then the variance of y will be equal to 3 square variance of z plus variance of 5.5 will be equal to 0. Constant will not have a variance. Mean of a constant is the constant itself. Variance of a constant is equal to 0. So variance of y will be equal to 3 square, that is 9 square, variance z, and variance z is 1 by 12. So 9 by 12 is what we have for sigma y square. So then we have the average over here, average being taken. So mu u is equal to mu y is equal to 7.0, and mu u is equal to, so to say, this is the standard deviation over here. So therefore, it is root of 9 by 1200. If you want just the variance, then it will be 9 divided by 12 divided by the value 100 over there. So this is the value of the standard deviation being mentioned over here. Then we'll have the first estimate the probability of P u less than or equal to 7.1 is what we have, and that is nothing but the CDF corresponding to 7.1, and that is phi of 7.1 minus 7.0 by the value of 0.0866, and this value, whatever is there for the corresponding to this, we need to see the table for the normal distribution, and we'll get the value which is something like this. The second part is for 1000 independent calculations. We need to multiply this figure by 1000, this figure by 1000 over here, and we'll get 876. 876. So if you see over here, this value should be, I think, root should not be there. It will be directly 120. So 0.5 by 120 is whatever value you got there. That is the value which you should write over there. If you write root of 120 over here, then that will just correspond to sigma y. So with this, we come to the end of this lecture. Thank you.